Sir, visible.
Okay. So today I will talk about regression analysis. So first of all, what we mean by regression analysis. So many times a measured variable is a function of one or more independent variables, right? For example, if you talk about a spring, you apply force. It is only a function of the displacement, right? The force is a function of displacement. But if you take an example of, let's say, pressure drop across a pipe, then the pressure drop is a function of many different variables. Okay. Now, when you sample the measured variable and you want to relate the measured variable with the independent variables, then you have to use what is called regression analysis. Okay, so let's say you have a dependent variable which is y, and an independent variable which is x, and you want to relate these two. So you have to come up with a relationship where you can express y as a function of x. Okay, now how do we sort of find this function? Okay, one simplest kind of arrangement that we can think of is a linear relationship. So we will take an example of a linear relationship and try to find out how a dependent variable would be related to an independent variable. And later we'll also talk about a case where a dependent variable will be a function of more than one independent variable. Okay, so before that, we need to talk about what is called method of least square, because regression analysis is based on the method of least squares. Method of least squares. So what is method of least square? Let's say you make some measurement for x. So you have measured data x1, x2 up to xn, right? So these are set of observations. Now, if you want to find the sum of squares of the deviation from the mean value, so we know that the mean value is the best estimate of this data set. And if you want to know the sum of squares of deviation, sum of squares of deviation, so we can find that the data point xi minus xm square, where your data point I would vary from 1 to n. Okay. Now, if you minimize this s, okay, sum of squares of deviation, you can write the minimization will be done with respect to the mean value. So you can write for a minimization of a function, the condition is that ds over dxm is 0, right? This is how we minimize a function x with respect to a variable xm mathematically. So when you write ds over dxm is 0, from here you would get that if you take ds over dm, so it will be I equal to 1 to n, um, 2 into xi minus xm into derivative of minus xm, so that will give you minus 1, So this is equal to 0, right? So if I expand this, I equal to 1 to n, so I have 2 into square root of xi, I equal to 1 to n. So 2 will go other side and become 0. So xi, I equal to 1 to n. Then minus, so xm will be written n times. So that is n into xm will be 0. So from here we can write that the mean value is sum of xi I equal to 1 to n divided by n. So this is basically nothing but the definition of mean value. Okay. So if you have n different data points from x1 to xn, and you say that my mean value is basically sum xi over n, in stating so, what we are trying to do is that we are trying to minimize the sum of squares of the deviation. So the mean value is a value for a data set that minimizes the sum of squares of deviation for that data set. Okay, so this is how one can understand the power of method of least square. Okay, so method of least square has been used to derive the definition of mean value. Okay, but that is not the objective here. Here, as I said, the objective is to relate a dependent variable with and one or more independent variables. First, we take only one variable and we say that the relationship is linear. Okay, so under that assumption, we talk about regression analysis using method of least square. So we talk about a linear regression. Okay, so let's say you have a dependent variable y which is related to an independent variable x through a relationship which looks like y equal to ax plus b. Okay, so this is a linear relationship between y and x, right? Linear relationship. Okay, now for a data set, you want to find out what this relationship is. So by method of least square, you find out S as the actual data point yi minus axi plus b. Okay, so if you have at a particular x, you are getting a particular y, right? Let's say this is current and this is voltage, or this is displacement and this is force. So for every x, you have a corresponding y, right? So this is something that you measure from experiment. Now, if you want to establish the relationship, so you write that let's say this is yi and this is xi. So instead of yi, you are basically writing axi plus b. Okay, so this is basically an approximation, but your actual data is yi. So if you use this relationship, there is some error that is going to come. What is that error? Error is this is coming from the fit and this is the actual data. So the difference gives you the error. Now sum of the squares of error. So you square the error and then you do that for the entire n data points, right? So I equal to 1 to n. So this is the sum of the squares of the error for this data set. Okay. Now, if you want to minimize this error, here you can see that there are two constants a and b. So you have to minimize the error by finding out A and B so that the error is minimum, right? So for that, you have to write ds over dA is 0 and ds over dB equal to 0. So basically, you are finding derivative of S with respect to A and another case B and equating that to 0. So in the first case, when you write ds over dA is 0, what will you get? So you have I equal to 1 to n. When you take derivative of this term, first you will get 2 into yi minus, I just open this bracket, axi minus b into, so derivative of dyi over dA is 0 and d axi over dA is basically minus xi, and derivative of b with respect to a is 0. So this should be equal to 0. So you are getting this from ds over dA equal to 0. Right? So this is basically giving you this. Now I can take 2 to the other side. So 2 basically is 0. So I have from this yi, or I can write yi xi. So if I multiply this first term here, sum, by default it is I equal to 1 to n, will be equal to, I take the remaining terms on the right hand side. So b into sum xi plus a into sum xi square. So this is one equation I get. Okay. Now, if I use the second condition, ds over dB equal to
Sir,
0,
one question.
yeah.
Do we get to further reduce it by removing xi in the
Yeah, yeah. So what we'll do is, see, xi you will not remove. Xi is basically known to you. Okay. So what we are going to get is we are going to get two equations and two unknowns. So unknowns are basically A and B. So we are going to express A and B in terms of the data xi and yi's. Okay.
Okay.
So ds over dB is 0. So if you take derivative of ds over dB is 0, so you basically get sum 2 into yi minus axi minus b. Then you get dy over dB is 0, d of xi over dB is 0, and then d of minus b. So that gives you minus 1, that is equal to 0. So this gives you that sum goes other side, becomes 0. So sum yi, I mean minus 1 also you can take other side, make it 0. So sum yi will be equal to a into sum xi plus b will be n times because this is I equal to n. So when you add n times, that will become n into b. So you get the second equation.
Sir, one more question.
Yeah.
Would it be n times b or sum from I 1 to n?
Yeah, yeah. So the basically sum I equal to 1 to n b is basically b you are adding,
Yeah,
n
yeah.
times.
Yeah, got it.
Okay. So this is the same thing. So you get basically two equations and there are two unknowns. Two unknowns are a and b. So you can easily uh, solve for a and b. So if you solve for a and b, I'm not going to follow the steps, but if you solve, you are going to find A and B as follows. So you are going to, sorry, we are going to get A as n sum xi yi minus sum xi into sum yi divided by n sum xi square minus sum xi whole square. So this is going to be your A. Okay. Similarly, you're going to get B as sum yi into sum xi square minus sum xi yi into sum xi divided by n into sum xi square minus sum xi whole square. So this is basically your B. Okay. So if you know A and B, you actually know the fitted curve. We call it y subscript c, that is the curve, or computed value of y for every value of x, right? X plus b. Okay. So now there are two things. You have for every xi, for every xi, you have a corresponding yi, but then you also have yci, which is computed from axi plus b. Okay. So now this is the data that you get from experiment. This is what you predict using this curve fitting. Okay. So you can estimate the standard error. So the standard error of estimate of y for the data by definition is given as yi minus axi plus b whole square divided by n minus 2 to the power half. So that is the formula for finding out standard error of estimate of y for the data. Okay. Now you can also, here we have done only y equal to ax plus b. Okay. But there will be situations where y may be a quadratic equation. Okay. So in that case, we are basically talking about a regression for a polynomial where you can express y as ax square plus bx plus c. So similar to the previous case, you basically find the sum of squares of error, that is I equal to 1 to n yi minus axi square plus bxi plus c square. And now you have three different constants. So you use three different conditions, that is ds over dA equal to 0, and this will give you some two into yi minus xi square plus bxi plus c into ds over dA. So only this term will stay, right? So that will be minus xi square will be equal to 0. Similarly, when you find ds over dB equal to 0, you will get sum 2 yi square say plus c into only this term is going to stay, right? That is minus xi will be equal to 0. Similarly, if you do ds over dc equal to 0, you are going to get sum 2 into only your this is dc over dc, so that will give you minus 1, right? That will be equal to 0. Now you have three equations, three unknowns. So these equations I will just write properly. So the equations that you are going to get will be equal to A sum xi to the power 4 plus B sum xi cube plus C sum xi square will be equal to sum xi square yi. Then A sum xi cube plus B sum xi square plus C sum xi will be equal to xi yi. Then A sum xi square xi plus C times n will be equal to sum yi. So these are three equations that you are going to get, and three unknowns, so you should be able to solve it. Solve for A, B, and C. So I do not have a closed form expression for A, B, C, but you can solve it. It's just three equations, three unknown. You can solve it. Now, one important thing I want to say about regression analysis is that when you write y equal to ax plus b, or you write y equal to ax square plus bx plus c, you basically assume that the uncertainty in y is actually more than that in x, which in other words, x is more accurately known than y, because you use the uncertainty in x to calculate y, so there will be uncertainty propagation. So definitely the uncertainty in y is going to be more than uncertainty in x, right? So when you do a regression, you naturally say that your x is more accurately known than y. Now there is one more thing I need to talk about before I actually take an example.
Sir, one question I have here is
Yeah.
Can I say that x variable or xi to xn whatever we
Yeah.
have can be measured directly by using an instrument, whereas the y is not able to be directly measured by using an instrument.
X is a
Is that right, sir?
dependent
Or y can be
variable,
also be measured by?
independent variable. Y is a dependent variable. Like I gave you the example of spring, right? So your displacement is X. The output is in terms of, let's say, some voltage is basically your Y. So X is, you are controlling it, right? You are extending it, the spring, and you are trying to measure the output. That is Y. So X is the independent variable, Y is the dependent variable. Okay.
Okay, sir. I had a confusion in that sense. Like if I can measure the y, then why should I estimate the value in that way?
So see, that is the whole point. The whole point is now, instead of noting down so many xi and yi, you are finding the dependency. If you plot xi here and yi here, how this curve is, whether it is like this, linear or power law, or what is the trend. So you are basically finding a fit, curve fit, or
Okay,
between y and x's. Okay.
right, sir. Right, sir.
So now if you found a curve fit, how good is the curve fit? How do you know how good is the curve fit? Typically, you use what is called correlation coefficient. Correlation coefficient characterizes the regression. It characterizes so you define R, which is 1 minus sigma yx divided by sigma yx square divided by sigma y square, 1 minus of that, half. Okay, so this is the definition of R. When you have done, if you have done some curve fitting in Excel, you must have found what is called R square value, right, for a curve fitting. So R square is basically square of this correlation coefficient R, and which is estimated as 1 minus sigma yx square divided by sigma y square. Now, what is sigma y and what is sigma yx? Sigma y is basically the standard deviation of y. So we know how standard deviation of y is found. So that is yi minus y mean square divided by n minus 1 sum half. We know that how we can find sigma y if you know all the yi's, right? You have xi, yi's. If you know all the yi's, you can find what is sigma y. Now, what is sigma yx? Sigma yx is basically the sigma value that is computed from the correlation. Okay, so this is the standard deviation which is computed from the correlation, not from the data. So sigma yx will be yi minus yi found from the correlation. Okay, square of that, sum it, n minus 2 to the power half. Okay, so for example, how do you find? So you have all the yi's, and corresponding to each xi, you will have a y value which is predicted through this curve, right? That is yic. You have yi. So you take the difference, square it, sum it up for all i's, and divide by n minus 2 and take square root, you get yic. So typically, you would have encountered when you do in Excel the r square value. So r square is basically square of that is sigma y square minus sigma yx square divided by sigma I square. Okay, this is called, R square is called coefficient of determination. Coefficient of determination. Now, if you have a perfect fit, right? Let's say you got 1, 2, 3, 4 as xi's, and your corresponding yi you got, let's say 0.1, 0.2, 0.3, 0.4. This is from the measurement. Now, using the curve fit y equal to axi plus b, you got exactly same value. So that means this quantity becomes 0, right? When this quantity becomes 0, your r square becomes 1, right? So when sigma yx becomes 0, that time your r square becomes 1. So that is a perfect fit. So when you do curve fitting in Excel, you are always looking for a fit which is giving you a higher r square value, and the highest r square value that you can get is 1. Okay, typically if it is more than 0.9 and 0.95, we say that okay, my fit is good. It is actually representing the data. So this coefficient of determination basically is characterizing the goodness of fit. Okay, if r square is close to 1, that means your fit is good. If r square is less, then your fit is not good. Okay. Now, even for a quadratic, so this is for a linear, when it is in axi plus b form. Now, this sigma yx, this definition whatever we are given, this is for a linear regression or linear fit. If you have a quadratic fit, for a quadratic fit, sigma yx will be yi minus yic divided by n minus 3, sorry, this square to the power half. So in general, for a polynomial of order m, okay, you will have sigma y comma x, sigma y comma x will be yi 3 divided by n minus m plus 1 half. That means when you take a linear fit, your m equal to 1, so you had n minus 2, right? In the previous example, previous case, you had it n minus 2 for a linear fit, and when it becomes quadratic, your m is 2, so it becomes n minus 3. If you have a cubic polynomial, something like ax cube plus bx square plus cx plus d, there your m will become 3. So that means it will become n minus 4 in the denominator, and so on. Okay. So in general, this is the correlation, the standard deviation that is computed taking the actual data of y and the computed data from the curve fit. Right, so let us take an example now. Go to the next slide and we take an example. Let's say we have the following data set. X is given in centimeter. It's some kind of displacement, and your output, you use some kind of force transducer, let's say, to measure this displacement. Your output is, let's say, in volt. So corresponding to 1 centimeter displacement, your output is 1.2. 2.0, it is 1.9. 3.0, you get 3.2. And 5.0, you get 5.3. So for every x, you have a y value, and you are asked to find an appropriate fit. Curve fit, assuming a linear relationship. Assuming a relationship between x and y. So first thing that we would do is that we would write our y fit. Let's say we write y subscript c is basically ax plus b, right? So we have to now go to our theory, where we wrote down the values of a and b. Here this is for a and this is for b, and so if I write down that, so first I write for a, is some xi some yi minus n some xi yi divided by some xi square minus n some xi square, and I just substitute these values. So you can find out some xi from here, right? These are all xi's, so you can find out some xi. Similarly,
15.
you can find some yi. If you add them together, you'll find some yi. Some xi yi is that you have to multiply them, right? You have to basically 1.0 into 1.2 plus 2.0 into 1.9 plus 3.0 into 3.2 plus 4.0 into 4.1 plus 5.0 into 5.3. So you can find out some xi is basically your 1 plus 2 plus 3 plus 4 plus 5. So you get some xi. Some yi is basically 1.2 plus 1.9 plus 3.2 plus 4.1 plus 5.3. So you can get this. And some xi if you know, then some xi square you know. And the only other thing you need to know is some xi square. Some xi square, how do you get? So basically 1 square plus 2 square plus 3 square plus 4 square plus 5 square. So you can calculate this. Okay. Now, if you substitute, so all the values you know for this equation, you have some xi, some yi, some xi yi, some xi square you know. And if this you know, then you also know some xi, some xi square. This also you know. N you know, n is 5. You have 5 data points. So I'm not doing the calculations, but if I substitute everything here, I would get A will be equal to 1.04. So this is something you can check for yourself. If I plug in all the values, I'm going to get A to be 1.04. Then I go to B.
Excuse me, sir. I have a question.
Yeah.
The equation that is in this page 6.
Yeah.
Previously, you have given the equation where n summation of xi yi minus summation of xi summation of yi. I think the equation is quite different from the earlier slide to the new slide. Is there any reason?
I think what I have done is I have basically multiplied -1 here and -1 here, right?
Yes.
That's all, right? I mean, it is the same thing, na? So
Okay,
if I think what you are saying is it is n some xi yi minus some xi some yi and some xi square minus some. They're the same thing, isn't it?
Yeah.
Just I multiply -1 in the numerator and denominator, so it is the same thing basically.
Okay.
Okay.
Sir, just a follow up.
Yeah.
So if we go by the equation from page 6, like our friend asked, it will come up to -1.04. So is it like we take a modulus of it, or
No. I don't think you will get -1.04 because both are interchanged actually. I'm multiplying -1 in the numerator, also -1 in the denominator.
okay.
Okay, you will get 1.04 only. So I have flipped both. So it is like A minus B by C minus D. I have written B minus A or D minus C. They're same thing, right?
Right.
Yeah. So I think to avoid confusion, let me do this. This is now correct, right? This is what it is. They are same thing. You will get 1.04. Please calculate and check. If you do not, then let me know. Now, I need to calculate B. Okay, so if I go to the here, so I have some yi into some xi square minus some xi yi into some xi divided by n into some xi square minus some xi whole square. So I'm going to write it here. So this is our B. This is our B, which will be equal to some xi square some yi minus some xi yi divided by n times some xi square minus some xi whole square. right? This is the same equation. Now, here also we have found almost everything in the previous case, right? You have some xi square, some yi, some xi yy, everything I have. So if I just substitute and calculate this, you check for yourself, then you can find that b will be 0.02. Okay. So essentially, you now have the fit. Okay. So the fit is YC is equal to 1.04x plus 0.02. This is the curve. Okay, linear regression curve. Now you can find out R, which I will not be able to calculate here, but you can do so. By definition, R square is sigma y square minus sigma yx square divided by sigma y square. So you can square divided by sigma y square. So how do you find sigma y?
We'll find the mean of the value that we have.
Yes, for each y, you basically find the mean. So your mean, y mean is sum yi divided by basically n. N is basically 5. So you can add all these here and divide it by 5. So you get the mean value. And for each y, you subtract ym from each y. That is your yi minus ym. And then you square it and add them up for each I and divide it by n minus 1 and take square root of that. And similarly, sigma yx, how do you find? So you have each yi here. So now this is basically each yi. Now you make another column where you yc. Okay, what is yc? Yc is basically your 1.04x plus 0.02. So for example, for x equal to 1, your yc will be equal to 1.04 into 1 plus 0.02, that is 1.06. So this you get as 1.06. Similarly, if x equal to 5, so you get your yc is 1.04 into 5 plus 0.02. So that is basically 5.2 0.02. So you get 5.22. So these are basically your YCIs. Okay, for each you can calculate. Then you basically write yi minus.
Sir, I think for 5 number you will get 6.572. Okay.
Sorry?
This value for the 5 is 6.3 multiplied by 1.04 plus 0.02. That will come around 6.572. Okay. Sorry, I just multiplied by 6. I'm sorry. You're right, sir. You're right. I did the mistake. Sorry.
Okay.
Sorry.
So you have this, and you sum it up, and here you have n minus 2. Okay. So this you can find, and you can find r square. Okay. And you can check that this value, how much it is coming. If it is typically greater than 0.9, there is no hard and fast rule, but typically greater than 0.9, then this fit is a good fit. So you can check it for yourself whether this fit turns out to be good or bad. Okay, so I will stop here, and we'll continue tomorrow. Next week again.
Thank you.
Thank you, sir.
Sir, one
Yeah,
request we have, sir.
Yeah, please.
I have. Sir,
Yeah.
basically, this subject is quite interesting and very new to us in that sense. Okay?
Yeah.
So there are some few key concepts where if you can just revise the, like taking half an hour in the next class, or maybe whenever you feel, sir. So if you just rebrief the key concept, that will be great learning for us, sir. Please, it's a request.
Okay, so what maybe in the next class we will be able to cover the first section of the course, that is the statistical analysis, because after that I wanted to go to the temperature measurement, pressure measurement, so measurements of various different kinds of quantities. So those I will be teaching mostly on PowerPoint. Okay. So
Okay,
I think once we complete the statistical analysis, I can have probably one class where I can briefly summarize, what all we have covered. Okay, give a brief overview of things that I think we have covered. Many things so far. I think we have taken about how many 6 classes now, including this.
Yes, sir. Yes, sir. 6 classes.
6 classes, right? So we will summarize, what all we have talked about till now.
so thank you for this kind gesture, sir. Thank you so much.
Thank you, sir.
Yeah. Okay. Thank you. Thank you very much.
Thank you.
Thank you, sir.
Bye all.